go. So good evening. It is November 9th. SC 416. Are you surprised at that? Nothing exciting here. Implementation report is due just before midnight. Code was due 45 seconds ago. And Canvas being Canvas, I'm sure it cut off right on time. Probably a minute early. Couldn't be anything too surprising here. The only thing that you should note, there is no class on Tuesday. It is a break. The self-assessment activity is thus due on Thursday. The Capstone Week 5 report is due on Thursday because today's part of the break. And your Capstone Project Team Declaration is due on Thursday at 5 p.m. After that point, I will manually create Canvas groups for everyone. So if you didn't sign up for a group, you'll be in a group of 1. Otherwise, you will be in a group of however many people you signed up to work with. Hopefully, I'll do that all right since I have to do it manually. Of course, every time I have to go through that, I think the whole reason we automate things is to minimize the likelihood that we're going to do them wrong. Of course, failure conversation, but first, this is not from Petrov or Klutman. This is from a couple of papers. The 2 papers that you are expected to read are the Byzantine generals problem, paper from 1982, like ancient history, and practical Byzantine fault tolerance, which isn't much better. It's 1999, still a long time ago. The paper from 1999 is important because for all intents and purposes, this is the paper that people go to when they're trying to implement a Byzantine fault tolerance system. What is it? Castro and Liskov. Barbara Liskov is one of the longtime distributed systems people. And her student Oki actually built a paper called View Stamped Replication in the late 1980s that implemented the Raft protocol 25 years earlier. In addition, if you are interested in this, I recommend that you look at the archive paper there. It's not actually peer-reviewed, but it is quite good. It talks about many of the things we've been discussing in this class, like linearizability, and how that applies in a Byzantine fault-tolerant system. Today's failure is an old one, but it's still a useful one. It was actually a bug in the Linux kernel that occurred on June 30th, 2012. Have any of you ever heard of leap seconds? So the time, I actually have heard one. I used to listen to WWV, and they occasionally introduce an extra second, and June 30th is one of the dates they traditionally do this on. I think they also do it on December 31st sometimes, but I know they do it on June 30th. And the reason for that is because the Earth does not rotate around the sun in exactly 365 days, and the Earth doesn't rotate on its own axis in exactly 24 hours. So when they first started numbering things in the Western world relative to the death of Christ, they didn't have leap years. They didn't add the extra day they have to add approximately every 3.96 years. And thus, what happened by the 17th century, the calendar was drifting quite far apart. I think it was 12 days. And so Pope Gregory actually corrected the calendar by adding 12 days in there. Now, I know these sorts of things because I've implemented actual clock algorithms where you can set the time. And dealing with knowing what all these rules are turns out to be much more complicated than like. So one of the things that you have to do when you write operating systems is make sure these sorts of things get handled properly. And unfortunately, in Linux's case, it didn't get handled properly. So what happened was we added the leap second. The Linux kernel didn't handle it properly, and it caused everything on the Linux box to wake up. This is a situation where all the threads that were sleeping, waiting for something to happen, all woke up and caused, and they checked to see if there was something for them to do. There was nothing for them to do, so then they would go back to sleep, and then they'd wake up again. This is it's called thundering herd, where you have things that don't actually need to do anything waking up. And some of this is ancient. It predates Linux. It was a problem in Unix systems where when you would sleep for something, we didn't make you sleep on the specific event. What we did was we mapped all of those events to a set of channels, and then we would wake up everything that was sitting on that channel. Well, that's fine if the ratio of events to channels is low, but then as our computers became more capable and we got more and more threads and more events that we could wait for, it led to this situation. I remember conversations and discussions about thundering herd from the ancient past. That would be the late 1980s and early 1990s, when, do any of you remember pthreads? So pthreads is a POSIX implementation of multi-threading. And originally, none of the kernel supported kernel-level threads. So pthreads was always implemented in user mode. Thundering herd was a real issue in these implementations. So it was something that came up in actual conversation and something we had to solve. But this isn't 1990, this is 2012. So the problem still happens sometimes. It caused massive CPU load, which in turn led to cascading failures. And you can read the article on Wired. Yes? It's actually kind of interesting, isn't it? It's hard to test. It's kind of like our distributed systems problems, where these failures are hard to test because they don't happen very often. In fact, it's really difficult to test these things. You end up trying to build scenarios. So I mentioned this before. One of the common techniques is to basically say, okay, I got this code. Let me set the clock to, I don't know, 5 seconds before this and watch and see what the system does across that boundary. I might not test the entire range there, but at least I'll have some basic idea that my logic has worked. I talked about wraparound conditions. Are you familiar with GPS? The Global Positioning Satellite System actually has a timestamp in it. The problem is that the timestamp is actually fairly small, and so it rolls over like every 12 years or so. And the software that uses GPS has to deal with that fact. How do you test rollover condition? The trick I learned a long time ago was initialize your counter not to 0, but to something just below 0, so that you would always have to deal with the rollover condition. So you can use defensive programming techniques sometimes to find these things. Otherwise, you end up trying to build scenarios where you can actually test, make sure that your software is going to handle the event correctly. But if you don't, then you're testing in production. And sometimes that just doesn't work out well. Question? Very common. Yes. It's a useful approach because it should work. And I'd look at it and I'd say, how do I make sure it will work? And I was doing this in a transaction log where I had a finite counter in my log, and eventually that was going to wrap. And I said, how am I going to make sure I deal with that case properly? Because part of it is when I'm doing recovery, so I have an epoch number, right? Every time I go through it simulates an infinitely long log in a finite amount of space. So each time you start back at the beginning, you increment your epoch number. The reason you have an epoch number is because when you try to recover the log, you need to find out where the most recent record is. And if you have an epoch number, it's super easy because you're just doing binary search. Half, half, half. You never have a large number of IOs, even for a fairly large log. But how do you know that's going to work right in the case where it wrapped? That was honestly my fear, was that it was like, this is going to blow up 20 years from now because this software will finally be stable enough that it will actually hit the rollover case. So I defensively programmed around it by making sure that it happened every single time I tested that code. It's not a panacea. You can't always do that. But in a case where you can do it, it's a really good trick to include. Just a little thing, but it makes your code more robust. I was the person who was, when I was dealing with adding time, made sure that I properly dealt with the fact that, you may not know this, but so you know that leap year is every year that's divisible by 4, unless it's divisible by 100, in which case it's not a leap year unless it's divisible by 400. Huh? So 2000 was a leap year. 2100 is not a leap year. 1900 was not a leap year. And that's because, remember I said it's roughly 3.96 years for the adjustment. Well, that gets us that adjustment the other direction, so we don't over adjust. And even that's not quite precise enough, which is why we end up having leap seconds. We have to keep adjusting the clock a little bit. This is another reason why we can't actually use the clock on the computer as our monotonic sequence, because the clock can go backwards, it can go forwards, it can do things that we don't expect, and we don't know how to reason about that. So that's why it's easier for us to just simply use a sequence number, because that's monotonic, at least until it rolls over. And you can reason about that particular case. So it'd be interesting talking about vector clocks and how you're going to deal with the rollover case, because you're using GPS, and the GPS clocks don't have infinite length. So as I mentioned last time, I'm moving away from a lot of the heavy stuff into some interesting topics. We're still going to be using the concepts that we've been talking about, but these are more specialized. The very first thing we did when we started talking about Paxos and other consensus algorithms is we said, we are not going to deal with the Byzantine case. We are not going to deal with message corruption. We are not going to deal with people who lie to us. Okay, well, we did that. We're more comfortable with where we are there now. Maybe it's still a little bit of a struggle, but we're a lot closer. And now we can say, okay, could we relax this? Could we do something in the face of Byzantine behavior? Does anyone know the etymology of the word Byzantine? Sorry? Right. The Byzantine Empire, which was well known for the fact that everyone lied to everyone else. That was literally the whole point of the term. This is a case where not everyone lies, but there are a lot of people who lie. So Liskov's work was to give us a real algorithm that we could use to implement Byzantine fault tolerance. It wasn't the first algorithm, it was just the first one that they were able to show was actually practical and did achieve its goals, which was to be able to handle up to some number of Byzantine actors. I had a friend who took a position at a US security agency with 3 letters and based out of Maryland. 3 letters are, the euphemistic joke is it means no such agency. I don't know if you've ever heard of that agency or not. Probably not, because it doesn't exist, right? And one of the things that she talked about, not very much she could talk about, but this is one of the things she talked about. She said when they got there, they were trained, they were taught that statistically they knew that at any point in time they had about 8 people inside of their organization who were compromised, who were actively passing information to third parties. So when you start pushing yourself into that thought pattern, it really does change the way you look at the world. You say, I really can't trust anybody now, can I? Definitely don't trust them. And you don't want to trust me, for sure. It was actually pretty interesting. It was when you realize that, it kind of changes your mindset. Oh, wow. The flip side of that, and this is one of the things that doesn't explicitly come out in the lecture, but when I was going through and trying to put the questions together for it, I said, that would be a really good question. Could I figure out who the Byzantine actors are based upon their behavior? Because the Byzantine actors are going to start lying. And it reminded me, I played this game called World of Warcraft. I don't know if you've ever heard of it, but in the previous expansion, they had one particular fight which was very interesting because two of the players would be taken over and they would lie. And so the key to this was some of the players could see who had been compromised. The two players that had been compromised couldn't actually see they had been compromised. They instead saw someone else. And so the question was, how many people need to point to somebody and say they've been compromised before you know that they're actually telling you the truth? And that is, in fact, exactly this problem. How do you identify the Byzantine actors there? Like, well, if you know that there's two compromised, then once three point their finger at somebody, you know that that's that person, unless one of the three people was confused, which did happen early on. People figured out you couldn't actually lie. You either knew or you didn't know. But it was kind of cool to see that used in a game of all places. And it's the same problem that we're working on here. What do we do about actors who are deliberately or inadvertently giving us misinformation? Finally, that's going to lead us into a much more jazzy, au courant version of Byzantine fault tolerance and distributed consensus, and that is blockchain. Blockchain is nothing more than a distributed consensus protocol that has a certain amount of resilience to Byzantine behavior. The motivation in blockchain is actually interesting because there is actually a financial benefit to convincing people of something that's not true. So how do we prevent that from happening? So to deal with Byzantine fault tolerance, what we want to do is remove that restriction from our previous consensus protocols and say, now what? What can we do with this now? The most frequently implemented version of this really is practical Byzantine fault tolerance. I would argue that blockchain is an alternative implementation of a distributed consensus protocol as well. And so maybe it's more well known than PBFT. I can tell you that PBFT doesn't burn as much electricity as Bitcoin. Almost nothing burns as much electricity as Bitcoin. So the big change to our model here is that our nodes continue to participate even after failures. Whether deliberately or accidentally, they are giving us misinformation. This could be simple, like, oh, there's a bad piece of hardware someplace that's flipping some bits and messages. And so the messages are coming through with the correct checksums because, of course, the bit flip is happening before we compute the checksum. But the message is now corrupted. Or it could be malicious behavior. You can't really tell the difference. So this is what leads us into this problem of the Byzantine generals. And the reason they like to use the Byzantine generals example is because it explains in real-world terms what the problem is, and it's literally in terms of a military outfit. You know, you've got generals trying to communicate with each other about when they're going to do certain things. How do we make sure that if you're going to attack, I'm also going to attack? So in the Byzantine generals problem, the question is, Do we attack the city or do we retreat? And we have multiple generals who have to make this decision. And if they don't all attack, then they will lose. So they need to make a consensus decision here. Everybody attacks, nobody attacks. Now, of course, you can look at this and you can say, well, if I had more than 3, or even maybe with 3, if 2 of the 3 attack, maybe I'll be okay. So there's going to be some numbers here about what will work for us. In the real world, where I'm sending messages back and forth, I am sending them via carrier pigeons, of course, right? What is that? RFC 1049? IP over Avian carrier. Great IP protocol, where you strap the messages to the leg of the homing pigeons. Then somebody gets the message and then they type it back in and it goes through the network there. It was written as an April Fool's joke. And then there are like a couple of additional RFCs that build on the April Fool's joke. So there's a quality of service RFC for IP over Avian carrier. Okay, so if one of these actors here is malicious, and or one of our messengers is malicious, one of our pigeons has suddenly been converted, swapped. He caught the pigeon and he changed the message on its leg and then he let it go free. How are we going to deal with that? The goal in building our Byzantine fault-tolerant protocol is that we still want safety. We still want liveness. But we also want validity. We want to make sure that we know how much error we can handle. See, that's what it ends up boiling down to, is how many people can lie, and we'll figure out the right answer anyway. If everybody lies, okay, we're not going to come up with the right answer. So there is clearly some threshold. If we allow some number of failures, in this case F, we have an asynchronous network, we allow Byzantine behavior, how many nodes do we actually need in order to guarantee a valid consensus? Well, how do we validate these things? So we can validate messages with cryptographic signatures. That will help protect us against certain classes of failures. So for example, each of the generals could have their own public key. And I can sign the message I send to you with my private key, and you can validate that by using my public key. So you'll know that it came from me. Well, so now we got rid of he trapped the carrier pigeon in the middle, because he doesn't have the private key, so he can't sign the message. So we can eliminate some classes of attack here. But we can't eliminate, and of course you can see how that gets rid of the general message corruption problem, but we can't get rid of or eliminate the possibility that one of the participants has been compromised. Now we're back to the NSA, where we know that there are some number of people who are actively compromised. Because you're getting paid a lot of rubles to do that. Hey, rubles are valuable somewhere. So what we need to do then is increase the number of participants. And it turns out the magic number is 3F plus 1, which is kind of interesting to me because it basically is, we needed 2F plus 1 to get consensus in the first place. So now we got 3F plus 1, so 1/3 minus 1. 1/3 of our nodes could be compromised. And we can handle that. So now we have a way of implementing a distributed consensus algorithm that can handle some number of faults. If there are more faults than that, we're not guaranteeing anything. The system can no longer guarantee that it will behave. So we've lost our validity guarantee. This protects us against corrupt leaders. It also allows us to, we use the usual trick for liveness, right? We have bounded delay. We're only willing to wait for your response for some finite amount of time, and after that we throw it away. Because Byzantine fault tolerance is not immune to FLP. If we allow arbitrary delay of the messages, we cannot guarantee liveness. So the paper by Castro and Liskov in 1999 at the symposium, what is it on? That's Operating Systems Design and Interface, OSDI. One of the big conferences, actually. The other one being SOSP. They used to alternate years, and then last year OSDI went to an annual format, and this year SOSP decided to go to an annual format, allowing PhD students to be able to publish more papers and graduate faster. The average for a systems PhD is about 7 or 8 years. Oh yeah. One of the really cool things about PBFT is that it's high performance. They can handle the F failures, so they can hit this number, and yet they do it with, in their implementation, 97% of the performance of a non-Byzantine system. That's pretty reasonable. They're losing 3% of their performance in order to work in a Byzantine environment. Now, this was a network file system protocol, aka NFS, which is still in use today. In theory, you should be able to take the PBFT implementation and run it. I think it was an NFS version 3 based protocol. So in the PBFT system, what we do is we have a replicated service. Our configuration is defined as a view, similar to what we did in Raft or view stamped replication. No surprise, view stamped replication was Liskov's work. In essence, we know who the leader is. So this is a leader-based protocol. The replicas are nothing more than replicated state machines. We should be comfortable with this at this point, because that's basically the model that we've been going back to over and over again. We are replicating logs. So we have a linearized sequence of events or operations. We are using integrity checks for our communications using public keys and HMACs, which are cryptographic hashes, because you don't sign the whole message. What you do is you compute a cryptographic hash and you sign the hash. That keeps the amount of overhead in doing the computation bounded. I don't know if have any of you ever worked with PKI? Public key infrastructure. Public keys, public key cryptography. Interestingly enough, there's about a 40% increase in the size of the data when you use PKI. Yeah, so you don't really want to make it for large blocks because you're sucking up a lot of extra bandwidth. Now, that number is based upon the specific algorithm, but the ones that we use here routinely, like RSA, have a pretty significant amplification of size. So the reason that we need to have 3F+1 is that it permits us to still find our quorum despite the fact that we have F bad nodes. That's what I found very interesting about this. It is kind of like what we needed for quorum anyway, and then we can just simply put some more nodes that we kind of just ignore them because they aren't voting in large enough block. So we need to have a quorum amongst n minus f nodes. In other words, we need a quorum inside of the non-Byzantine nodes. Okay, and we have enough. And one of the things I like is, because the way I've been talking about this is quorum. So this is, again, just a quorum model. By not focusing on majority, but instead focusing on quorum, it makes it easier to understand what we're doing here. There's no other set that you can pick here that isn't going to lead to the same agreement. Because to pick the wrong value, you need more than F. The flow through these things isn't really radically different than it was in any of the other protocols where we send a request out and then we get the replies back. And once we have the replies, we get F plus 1 of them. We now have enough replies, and we know that we have consensus. Kind of cool. We can use a three-phase commit style protocol here, which is request, pre-prepare, prepare, commit, reply. That's what practical Byzantine fault tolerance is. There is an interesting paper by Lamport. I considered throwing it out, but it's a page and a half long, and it's mostly the details are left as an exercise to the reader. So I was like, yeah, probably not very useful here. But I think it might make a really good question on the final. Suppose you wanted to make Paxos Byzantine fault tolerant. How would you do that? How would you design a Byzantine fault tolerant Paxos protocol? That's a good question. The pictures, by the way, are actually borrowed from the original paper. Why redraw them? So in the pre-prepare phase, what's happening is that the leader is sending out the request, including the message that's going to be processed to all the backups. The leader then records the message in its log, and then the replicas either accept the pre-prepare message if it validates. Message validates, it's signed properly, the HMAC is correctly signed, and the view number is correct. So in other words, we haven't had a topology change here. We haven't changed leaders. Everything looks good. And so we collect up the votes, and we make sure that the answers that we get back, let's see, actually, that's still the pre-prepare. All the pre-prepare messages are within the acceptable range of proposal numbers. And then we tell the proposer, yes, we've accepted your proposal. In this case, there's only one proposer, it's the leader. So once we get the pre-prepare messages, then the replicas send a prepare message. They accept the pre-prepare, then they send a prepare message. Now notice it's the replicas that send it out this time, not the leader. The replica says, okay, I've accepted this pre-prepare. You should prepare to handle this particular case. And now we wait for the consensus to form. And the consensus here is, do enough replicas agree? F plus 1. Do enough replicas agree? And when we have that, actually it's 2F, sorry. When we have that, then we know that it's been accepted by all of the replicas, or by 2F plus 1 of the replicas, which is all we need. So now that we've done that, we need to tell all the rest of the world what's actually happened, and these are our commit messages. So we say, yes, the prepare was accepted by 2F, and we send that out. So prepared is true, and we have 2F plus 1 committed messages. And now we can reply to our client. That guarantees our client that we've reached consensus. We've decided what the value is. We've accepted your command. So in this particular case, what we've decided is what's going to go into the next log slot. Same as we did with Paxos and same as we did with Raft. Well, I can't do anything. I'm always very clear that this is, there's not much I can do if it goes down in the middle of a class. I mean, I can come over here and I can say, yeah, it dropped the Wi-Fi. It says there's Wi-Fi available, but it disconnected. Can't connect to the Wi-Fi. I have no idea why it just randomly drops like that. I think the last time it was because whatever the time was window for accepting the certificate, because UBC uses a self-signed certificate for their Wi-Fi, had expired. And so then you have to forget that connection and sign in again and then accept the self-signed certificate again. Yeah, it's not. I'm trying UBC Secure this time and it's not doing it. Well, it's going to be recorded, so. There are lots of details in the paper about practical Byzantine fault tolerance, including how you garbage collect the log. Because remember, you can't garbage collect the log until everybody knows what the outcome was. Otherwise, you won't be able to get the quorum that you need in order to verify that this was an accepted value. It talks about view changes, i.e. what happens when the current leader fails and we have to switch to a new leader. It's not super interesting for our conversation today because we've gone through leadership change. So you should be comfortable with that. It's not really any different here. Liveness is discussed in the paper, why this will continue to make forward progress. It's basically using the same technique we've been using in our other consensus protocol. So again, nothing that I want to dive into in this conversation, but it is described in the paper as well. There are lots of performance optimizations. The way they got 97% performance optimization was because they eliminated an awful lot of messages. I've talked about some of the kinds of things that you do to eliminate messages. So for example, I send a proposal. When I send a new proposal with a higher number and a different value, you can implicitly assume the previous proposal was accepted. Right? Those kinds of tricks. We can infer what happened rather than have to explicitly send a message. So usually when you're designing this kind of a protocol, you sit down and you specify everything. I send a proposal, you send an accept, I send a commit. And then you look at that and you go, but the next thing you're going to do is send a new proposal. If you send a new proposal out from a different client, I can just assume that means the previous proposal was accepted. And now I've eliminated a message. And by eliminating that message, I've increased the performance of the system. What other places could I do that? This particular protocol had an awful lot more messages, so there are optimizations that you can make to it. And finally, their replicated NFS service is what was interesting, I thought, about this paper. I'll look to see if the network is still whining. It probably is, but what the heck? No, it says it connected. It connected back to Eduroam, the one that it disconnected from previously. Because I tried connecting to here, so maybe the stream is back up. That's okay. When I get done, I'll have a whole series of emails from Twitch telling me about all my streams that have completed. Blockchain. I don't even remember where I stole this particular picture from, but it was a great picture. Just kind of talking about what blockchain is. Has anybody heard of blockchain? One person. How many of you have traded cryptocurrency? Come on, admit it. I have a friend who paid his undergraduate tuition by mining Bitcoin in the university's computer lab. Does that tell you how long ago it was? It was more than 10 years ago. But it turns out that like in the 2011, 2012 timeframe, you could do that by mining on CPUs. Have any of you ever done mining? You have quite an power bill. Are you in the dorm maybe? So you can use... So you weren't doing Bitcoin then? Yeah, I was going to say, because so the interesting thing about Bitcoin, and I started looking at this in the mid 2014, 2013 is when I started mining. And I looked at buying mining rigs, and basically my conclusion was that if the mining rig was 1 month late, you'd never make money on it. Literally, they were adding so much hashing value to the network at that time that you couldn't make money if it was delayed by 1 month. That almost all of your profit was in that first month. And you'd be lucky if you could pay for the mining equipment after that. Today, you can actually buy mining equipment pretty cheap. The most expensive part about mining equipment is the electricity it costs to run it. So if you're in the dorm, yeah. So it turns out that BC had quite a lot of interest in Bitcoin mining because you could take mining rigs and put them next to hydroelectric dams. You'd get about 1/3 more electricity for the same price because you didn't have transmission loss. You probably don't think much about how electricity gets from where it's generated to where it's consumed, but it's quite a complex business. I was involved in a case a couple of years ago where it was about trading of the right to transmit electricity over pieces of the grid, and people make big bucks on that. Very interesting. A lot of quantitative analysis in it. What was the problem that cryptocurrency was trying to solve? What? Why? Right. So, in fact, the idea behind having a digital currency is not a new one. It was proposed in the 1990s. There was a guy named David Chaum who proposed a series of these things. And the biggest problem they had with any kind of electronic or digital currency was that I could present it to two people at the same time and do the double spend. And so the question was, how do I prevent double spending without a centralized authority? It's easy to prevent double spend with the centralized authority. And governments didn't really care about that because they were the centralized authority. So they're perfectly okay with the centralized authority model. The decentralized authority model is the one that we use in a true blockchain. No single centralized decision maker. It's Byzantine because we have a fundamental problem, and that is people want to spend the same money twice. Oh, look, I got copies of my money. Here, I'll pay you with this 50 and you with that 50, and it's the same 50. Life is good. And, I bought a pack of gum, so I got 49 back from you and 36 back from you. Who was more expensive? But I got different currency back. And so how do I prevent that from happening? Question. Actually, that is an interesting problem, yes. So the question was, does that mean that you end up with it, if a bunch of people control it together, do you end up with a centralization? Yes. One of the weaknesses of Bitcoin is that if any one party or any colluding party controls more than 50% of the blockchain, then they actually can rewrite history. And there are a couple of times when the control of the blockchain has gone over, not a lot, but just a little bit over 50%. And actually, they have broken up the pools that ended up with those majorities. And the reason for that was because they knew it would undermine the confidence in the actual cryptocurrency. He was using GPUs to compute SHA-3 values. So that's why you know what SHA-3 is. Because SHA-3 was explicitly designed so that you couldn't actually build ASICs, which is what SHA-2 and Bitcoin miners use. SHA-3 uses a completely different kind of function. It's not amenable to hardware-style solutions, but it is at least somewhat amenable to using GPUs. And so for a long time, Ethereum, which is an alternative blockchain, was using GPUs to compute a particular problem. I'm going to talk about that problem in a minute, but I just want you to basically get a high-level understanding. Kind of a cool slide. It's got lots of details in it, but let's dive into this a bit more. So in 2008, this anonymous person, whom we still don't really know who they were, Satoshi Nakamoto, wrote a paper, a white paper, titled Bitcoin, a peer-to-peer electronic cash system, in which they proposed a distributed consensus algorithm that was Byzantine resistant, that would allow for cryptocurrency. Well, see, the network issue is back, so it tells us right there, network issue. Yeah, huh. Weird. I don't know. Well, that's what they get for not showing up for class. I'll watch it on YouTube. What is a blockchain? Basic idea. So in fact, the basic idea in a blockchain, especially for cryptocurrency, is a fundamental idea in modern accounting practice. Anybody familiar with accounting? So in accounting, we have transactions. And one of the things that we do is we organize all of our transactions. We say, okay, so something came in and something went out. And in the end, those things have to balance out. That's what's called a ledger page. So in a ledger-based system, we have a way of validating that the information that we've entered into the ledger balances and thus is correct. It's this very simple mechanism for ensuring correctness that can be done by hand because ledgers have been around longer than computers. I mean, I was looking for slides on this again today, and I didn't find anything super inspirational, but there were pictures of ledgers from like the 18th century. And we know that ledgers were used before that because they are fairly commonly used in historical research. When we can find them, they're often a treasure trove of information about very mundane details of old societies. Pretty cool. Well, we're going to use the same basic idea, the same basic principle in building our blockchain. So that's our balanced set of operations. Another interesting thing about blockchains is they are public. They're publicly visible. If you want to download the entire Bitcoin blockchain, you can. All, I don't know ever how many gigabytes, probably over a terabyte by now. Download the entire chain, the whole thing. You don't have to. Use Merkle trees and whatnot to allow you to look at just pieces of it and still know what's going on. It's also easy to verify. The interesting thing about having a cryptographic hash on an individual ledger page is it's not that expensive to compute. It's easy to verify. You're going to have a problem that will not be easy. And that's going to be part of what makes Bitcoin in particular an energy-wasting pig of a service. You can think of Bitcoin as implementing a distributed timestamp service. It linearizes the operations. It's doing the same thing that we did with Paxos, except, of course, it's just a slightly different format. We have this Byzantine assumption, and it involves money. Virtual money. I've had these fun conversations about what's real money and versus what's virtual money. People are like, well, it's not real. I'm like, okay, and when the money is in your bank account, it's not real either. It's just numbers in a ledger someplace. People don't know how to respond to that. So the thing that makes it a chain is we take these ledger pages. We have a ledger full of transactions, and we compute a hash. We incorporate the hash value of the previous block in the ledger and everything that's in that block, And that gives us a new hash value, which we use when we hash the next block. Hence, each block is tied to the previous block, and the blocks subsequent are tied back to that block. So it creates a chain. The reason that this is important is because we are going to make it hard to compute a hash that passes the requisite check. How do we do that? Kind of clever, actually. We have a small field in the block that isn't part of a transaction. It's a piece of metadata called the nonce. And that piece of metadata can be manipulated in such a way that the hash value that is computed meets a specific set of requirements. The number of 0 bits in the front of that hash value. It doesn't actually matter whether it's front or back. It's the same exact problem, but so it's the high order bits. This is called the difficulty. And only way to figure out a hash value with a nonce, because it's the nonce that you change in order to get a different hash value, the only way to figure out a nonce that will meet the difficulty requirement is to try. Talked about MapReduce. It just becomes a massive MapReduce problem, except that instead of us adding up links and whatnot, what we're doing is saying, hey, you try 0, 5, 10, you try 1, 6, 11, you try, so you just break up the search space. And you literally just keep trying different nonce values until one of you finds a nonce value that actually meets the difficulty requirement that's current, part of the configuration of the system. And then you announce that you have found a solution to the current set of transactions. It's a little more complicated than that, because it turns out that I don't have to be working on the same set of transactions that you're working on. The way that it works, in fact, is like in both Ethereum and in Bitcoin. If you want a transaction to be added to the blockchain, you send it out. You're a client. You start saying, hey, can somebody here pick up my transaction and put it into a blockchain, and I'm willing to pay you so many Satoshis to do it. Okay, I know how to optimize this. Take all the current offers that have reached me, sort them from most Satoshis to least Satoshis, take the top N that fit into the block, and the rest of you guys, you can fuck for it. There's actually people who study how long it takes for transactions to get put into the blockchain, depending on how much you offer. So when the blockchain is very busy, people pay a premium to get their transactions into the block, because it's a fairly small block. It's about, I think it's 2 meg, if I remember correctly, 2 megabytes. It's not a lot of transactions. But you may know about different transactions than I know about, so our proposed ledger pages can be different. It doesn't matter. The first one of us who gets to a valid block gets to propose our block to the network. Now, there's an interesting balancing trick that ends up happening here, because if I compute a block, I can flood it out to the network right away, or I can try and game the system a little bit, because remember, this is Byzantine. Kind of stuff really happens. I can say, how about I start working on the next block? Maybe I'll hold this block for a little bit until I hear somebody else try to flood their block out, and then I push mine out. And people literally do this. Or maybe I say, well, okay, I want to at least use that window. I'll start pushing mine out, and I'll start computing the next block. That's just a presentation, isn't it? So there are benefits to being the party that ends up proposing the successful block. You, in essence, get a small head start on the next block. Pretty small, but it's large enough that miners create what are called mining pools. They cooperate in figuring out who takes which hashes to check. If we're all working independently of each other and we all end up with pretty much the same set of transactions and the same mappings and whatnot, then a lot of us are going to be searching the same space. It's going to be even less energy efficient than it already is. There are reasons that it makes sense to work cooperatively in groups. And then what happens, of course, is that when you get a block, so one of the entries in that block is actually new coins that get created. And the number of acceptable new coins continues to go down. Every 2 years, it decreases by 50% until the last division, which is, I don't know, another decade away or something, when there will be 21 million Bitcoins. So what does a miner get? A miner gets paid the fees for the individual transactions plus the coins that they've mined. That's why it's called mining, because you create new coins in the Bitcoin system. And the reason that Nakamoto proposed doing it this way was because it rewarded miners early on, so it made the system valuable. And given the current price, what is the current price of Bitcoin? Anybody know? Probably. Yeah, it's a lot of money. I mean, you read about that guy who's got like $300 million worth of Bitcoin on a drive that he can't unlock. He's got 2 more guesses and then it's gone. Like, oops. I hate when that happens. So it's a fairly simple idea, but it has a lot of really powerful implications. Like I said, it's all based on this basic idea of ledgers. I managed to find some cute little graphic of a basic accounting ledger, and that's really all we're talking about. Conceptually, that's all this is. The details are different. It doesn't matter. Conceptually, it's just a list of transactions on a page that have to balance out. That nonce is known, and the hash computation is known as proof of work. So your proof that you have actually done something of value to earn your fees is that you have a valid block in the blockchain. Did I mention that the only way to find that nonce is guess? And you guess and it's wrong. You guess and it's wrong. And you guess and it's wrong. And you guess and it's wrong. And eventually somebody guesses and they get a nonce that's right, a nonce that works. Every time we run that computation, it costs electricity. Bitcoin miners are ASICs. They are custom processors. They use very large power supplies. They're noisy. And they consume huge amounts of electricity. Like the equivalent of some countries. The downside to blockchains is that they can grow. Remember, I said it's this whole public ledger. In theory, you can download the entire ledger, but they use Merkle trees to allow you to prune out parts of the tree that are dead, basically used as a garbage collection technique. So you can kill things that are no longer needed and only keep the pieces that actually do. Right now, there are people who still store the entire Bitcoin blockchain. There are reasons that you might want to be able to do that because it is a public ledger. If you work in forensic analysis of blockchains and do routinely track backwards, the place where you catch people when they're using Bitcoin for things that are unlawful, when they try to convert Bitcoin into fiat currency, aka Canadian dollars, US dollars, Chinese renminbi, Russian rubles, North Korean, whatever they use. I don't know what North Korea's currency is, but it turns out that North Korea is very active in blockchain, interestingly enough. But it's a public ledger. And so you can analyze it. You can actually track transactions through it. And there are people who are pretty good at it. But not all of the blockchains provide this kind of or transparency. Monero is well known being one where the transactions are, in fact, much more anonymous. But the weak spot in all of these systems ends up being the conversion of the cryptocurrency into fiat currency. So blockchain is a distributed consensus protocol that is Byzantine resistant. There are pros and cons to these. PBFT requires a lot of extra nodes. Blockchain is actually not, it doesn't have that requirement because of proof of work. The proof of work actually buys us an interesting solution out of the node count. So we burn lots of electricity instead of having lots of nodes, although blockchain still has a lot of nodes. Why we're burning so much electricity. So I'm not sure that's a huge. Communication costs in PBFT are actually pretty high. One of the grad students in our group, in our research group, actually published a modification to the Bitcoin protocol that decreased the communications overhead, and it's been adopted as part of Bitcoin, the actual Bitcoin protocol now. It's a very interesting bit of work. So blockchain is not quite the same as Bitcoin. Blockchain is more general than Bitcoin. Bitcoin is a particular instance. Nakamoto wrote about Bitcoin, but he introduced the idea of a blockchain. Since then, other people have come along and used this. Let's see. The interesting thing about Bitcoin and blockchains in general is they've actually done a pretty good job of encouraging people to behave. Because yes, you could do Byzantine things, but even in blockchain, rewriting history is very hard. The farther back you want to change it, the more computationally prohibitive it becomes because you have to recompute. Let's say you decide to change a block from yesterday. You have to recompute everything from yesterday to today. And the blockchain continues to grow, because the goal in Bitcoin, at least, is that they generate a new block every 10 minutes. So you need a huge amount of computational power just to catch up on 24 hours, because you've got 6 additional blocks every hour. And you burned enough electricity to power Germany for the evening to compute that one block in the blockchain. So to catch up requires a lot of extra power to do that. It makes it inherently resistant to tampering. Ethereum has moved to a different model fairly recently. They have moved away from a proof of work model, so your GPU mining is no longer useful. Now you need to be buying lots of Ethereum. Right? And instead have moved to a proof of stake model, which is what I think of as the oligarchic model. The people who have most of the Ethereum get to cast the votes about where the Ethereum is going to flow to next. It does have the same kinds of problems around collaboration. Too many people agreeing cheat. And that's one of the reasons it took them years to agree on how to do that. They have some mechanisms for making that less likely, but that is not my area. If you want to know more about some of these things, I think I've mentioned Algorand before. Algorand is really cool because Algorand is a majority Byzantine environment where they were able to tolerate up to 2/3 of the nodes being Byzantine and still successfully achieve consensus. Algorand, the company, is a DeFi company. What is that? Centralized finance. Ethereum moved to proof of stake. You might also know Ethereum because it's primarily where NFTs are implemented. I don't know if any of you know what NFTs are. Maybe you remember a couple of years ago, there was this thing that they helped build here in Vancouver called CryptoKitties. CryptoKitties are still around, by the way. They're actually NFTs on the Ethereum blockchain. There are lots of fun things that you can do in Ethereum. There are people who have actually found that there are pornographic images on the Ethereum blockchain. It's actually an attack mechanism, poisoning mechanism. If you put child porn in the Ethereum blockchain, you can't get rid of it. You can use this for land title registry. In places where land titles have been subject to tampering, having a blockchain-based distributed titling system can actually be beneficial. There are lots of interesting problems around this, but there's a paper on it. I think I mentioned this earlier in the class too. So what did we talk about? Oh, and I stole these slides from the last term because none of this has changed. And this is just an interesting side topic. We talked about Byzantine system, talked about PBFT, and we talked about blockchain. Any questions? Besides what's for dinner? No, after 6. Yes. How rewriting the blockchain will work. So, right. So let's suppose that you actually have 10x the compute power. You decide you're going to go back to yesterday and you're going to change one of the blocks. So then you have to take that block and recompute it. And then now you have a new hash value, so you have to take the next block and recompute that, which means you're going to end up with a different nonce. And you have to do that fast enough. Yeah, you have to recompute every single block. That's why it becomes impractical fairly quickly. In blockchain, right now, the computational limits say that by the time 6 blocks have gone by, a transaction is hardened. And it's not practical under any scenario. We don't have that much compute power for anybody to ever catch up. Maybe a better example or a different example of this is, for example, in Bitcoin, when they split and they did Bitcoin Cash. Hey, I ended up with both, right? So I had both. I had Bitcoin. I ended up with Bitcoin Cash, which I sold, and I had regular Bitcoin, which I sold because I look at this stuff and I go, this is like, doesn't make any sense. Like Vancouver real estate, right? Doesn't make any sense to me. Why would I put my money into it? I mean, I bought my first Bitcoin at $130. Well, I sold it at 7,500. I was like, I never wanted to put that much money into it because I wasn't willing to take that much risk. I'll have some somewhere in one of my wallets. I'd say the biggest use of, one of the bigger uses of cryptocurrency are in fact illicit transactions. I was reading a whole article about yesterday about what's called pig butchers. In pig butchering, they actually hire, well, or recruit people to run social media scams. Literally, like in Myanmar, they take people and they put them in semi-imprisonment, and they make them get online and chat with people on Tinder and whatnot. Try and convince them to, they try to gain your trust, so that then they can get money out of you. Because the article in question that I was just reading was from the Wall Street Journal, where some woman lost $1.6 million US. I have a friend whose father was swindled out of £250,000. Oh, and he kept going back too, because, you know, very, very strange. But yes, and that is how they launder the money. They launder that money by quickly converting it into Bitcoin. It used to be that people wanted you to just Apple gift cards to settle your CRA bill, because CRA. But in fact, now what they do is they try to convince Bitcoin. I find it kind of interesting. I've actually had people try to fish me like this. Like, I've played them, figure out what the angle is, and it's sort of interesting. I find that I'm an old fat dude, right? So they think I'm a mark, and I find it fascinating to see how they perceive. one today. I sent him the article from the Wall Street Journal on pig butchering. Blocked me. Great, this is awesome. Usually I can tell within like 2 sentences. I don't know. It's a real problem. So there are interesting uses for blockchain, but if you actually want to do any of the trading in this, be careful because you probably are, somebody's going to try and take advantage of you. And it's not just social media scams. It's people stealing wallets is a very big thing. There was you probably remember Mt. Gox. Right. So Mt. Gox actually ended up getting ripped off. Somebody stole a whole bunch of Bitcoin from them. Now, here's the interesting part. The authorities were eventually able to recover some, like 10% of the actual Bitcoin that was stolen, and it was more than enough to pay everyone back because the value of Bitcoin had gone up so much between the time that Mt. Gox collapsed and was seized. People didn't get all their Bitcoin back, but they got their money back. How's that for crazy? You gotta. Right, and I actually am not sure how Monero does that. I haven't looked at it specifically, but like you, I know that that's the one where you can't track things. They do provide anonymity of the transactions. Why are you mining Monero now? Maybe. Correct. They used to use Bitcoin, but it's not a very good choice because when you're trying to, hire somebody to kill your spouse, it leaves too many footprints. Kind of like any kind of money laundering, right? Where you split it up and you divide it into multiple wallets and try to put it back together later. Cross cryptocurrency trading is another way to do that because that makes it very hard to track. Again, eventually you have to take the money out, and that's always the interesting point. Had Twitter call me several years ago because he wanted me to look at ledgers for some guy who was Nigerian prince. I made that up, but I didn't. Who claims that he had been getting money from people in Nigeria, buying used cars, and then shipping them to Nigeria. And ostensibly, he had this ledger Bitcoin transactions because the trick is he got caught with 300,000 US in cash on a Native American reserve in Nevada. And they claimed it was drug money, and he claimed that it was money. And he was coming back from Colorado. And so, in fact, the whole thing made sense because who has a lot of cash and not an easy way to convert it into something that's not cash? Marijuana dispensaries in Colorado because it's all in cash and they can't bank. And so it kind of made a certain amount of sense. But then they sent me these things, and they were like Nigerian bank records. Aren't going in the ledger. Never heard back. I think he was trying to pull on his lawyers, but very interesting when you sort of rub up against some of these things in the real world. Well, I think that in fact there's a certain incentive for the tribal police to want to keep the cash, as of course they can use forfeiture as fruits of criminal behavior. $1,000 is a spendable amount of cash. That was U.S. cash, by the way. And it's not like this Canadian stuff, which is worth like 75%. All right, that's it for today. See you guys next Thursday. Enjoy your break, because I'm sure none of you are going to be working over the break, right? Not just an excuse for, oh my gosh, I'm going to try and catch up. Oh, screw that, I'm going to game instead. Right. Well, then it really is a break. Maybe you don't game. Okay, good. It's good for you. And there's this collection of Werther originals here that they're not mine, they're just sitting here in case you feel the need for sugar. And we're done. I have no idea if the streaming ever